Hey everyone, welcome back to Chem Story. Today, we're talking about hybridization, how carbon's orbitals mix to form bonds. This concept helps us understand why carbon forms stable covalent bonds and why molecules like methane, ethane, and ethine have their unique shapes. So what makes carbon so good at bonding? It all comes down to its orbitals and how they hybridize. Before atoms form covalent bonds, something interesting happens. Their atomic orbitals go through a process called hybridization. So what does that actually mean? Instead of using their original orbitals as is, the atom mixes them to create brand new orbitals called hybrid orbitals with different shapes and directions. And this isn't just a random rearrangement. It has a purpose. Hybridization helps create unpaired electrons, which are exactly what atoms need to form covalent bonds. Take carbon, for example. Through hybridization, carbon ends up with 4 unpaired electrons, so it can form 4 strong covalent bonds. That's a big reason why carbon is so good at building all kinds of molecules, and why it's the backbone of organic chemistry. For second-period atoms like carbon, the s and p orbitals can mix together to form what we call sp(n) hybrid orbitals. The value of n depends on how many p orbitals are involved. It can be 1, 2, or 3, and based on that, we get 3 main types of hybridization. In sp3 hybridization, 1 s orbital and 3 p orbitals mix, creating 4 equivalent sp3 orbitals. In sp2 hybridization, 1 s and 2 p orbitals combine, forming 3 sp2 orbitals, and 1 p orbital stays unhybridized. In sp hybridization, 1 s and 1 p orbital mix to form 2 sp orbitals, leaving 2 p orbitals unhybridized. Now, here's something really important to keep in mind. Any p orbitals that don't get hybridized can still participate in bonding, but only as pi bonds, and only if they have unpaired electrons. This is exactly what we see in molecules with double or triple bonds. Another key point about hybridization is the energy of the orbitals involved. When hybrid orbitals are formed, like sp, sp2, or sp3, their energy lies somewhere between the original s and p orbitals. Now, here's something interesting. The more p orbitals that are left unhybridized, the higher the overall energy tends to be. That's because unhybridized p orbitals form pi bonds, and pi bonds are higher in energy than sigma bonds. So as we move from sp3 to sp2 to sp hybridization, the number of pi bonds increases, and the overall bonding energy goes up as well. All right, now let's move on and take a closer look at the different types of hybridization in a carbon atom. All right, let's start with how sp3 hybrid orbitals form in a carbon atom. This is super important for understanding how carbon forms 4 equal bonds and why molecules like methane have the shapes they do. So here's what's happening. Carbon has 6 electrons total, and in its ground state, its electron configuration is 1s2, 2s2, 2p2. That means, in the second energy level, there's 1 2s orbital with 2 electrons and 3 2p orbitals, but only 2 of those p orbitals actually have electrons. So right now, we've got 2 paired electrons in the 2s orbital and 2 unpaired electrons in 2 of the 2p orbitals. But here's the problem. If carbon only has 2 unpaired electrons, then it could only make 2 bonds, right? But we know that carbon can form 4 bonds, not 2. So clearly, something has to change. To fix this, one of the 2 s electrons jumps up to the empty 2p orbital. This is what we call excitation. Now, instead of just 2 unpaired electrons, carbon ends up with 4 unpaired electrons, which means it's ready to form 4 bonds. After excitation, the electron configuration becomes 1s2, 2s1, 2p3. So now we've got 1 electron in the 2s orbital and 1 electron in each of the 3 2p orbitals, giving us a total of 4 unpaired electrons. But here's the thing. This setup still doesn't explain how carbon forms 4 identical bonds in molecules like methane, and this is where the magic happens. So what happens next? The 1,2s orbital and the 3, 2p orbitals mix together, and they form 4 new orbitals called sp3 hybrid orbitals. These new orbitals are all identical in energy, and they arrange themselves in a perfectly symmetrical shape. Now, instead of having separate s and p orbitals, we've got 4 matching sp3 orbitals, each holding one unpaired electron and each one ready to form a bond. These new sp3 hybrid orbitals are made up of 1 part s character, that's about 25%, and 3 parts p character, which makes up the remaining 75%. And because of this mix, they naturally arrange themselves in a tetrahedral shape, spreading out as far apart as possible to minimize repulsion between electrons. That's why molecules like methane take on that classic tetrahedral geometry. It's all thanks to the shape of these hybrid orbitals. Now that we know how sp3 hybrid orbitals form, let's see how they actually work in real molecules like methane and ethane. In methane, carbon goes through sp3 hybridization and forms 4 identical sp3 orbitals. Each of these overlaps with a hydrogen 1s orbital, creating 4 strong sigma bonds. This gives methane a tetrahedral shape, with bond angles of about 109.5 degrees, and that makes it super stable. Now in ethane, we've got 2 carbon atoms, and each one forms 4 sp3 orbitals. 1 orbital from each carbon overlaps to form a cc sigma bond, and the remaining orbitals bond with hydrogens, giving us 6 CH sigma bonds in total. And here's something cool, that cc single bond in ethane can rotate freely, which makes the whole molecule a lot more flexible. Now, let's move on to sp2 hybridization and see how it shapes molecules. In sp2 hybridization, 1s orbital and 2p orbitals mix together, forming 3 equivalent sp2 hybrid orbitals. But here's the important part. 1p orbital doesn't hybridize. It stays as it is, and it's positioned perpendicular to the plane of those 3 sp2 orbitals. That leftover p orbital can overlap sideways with another unhybridized p orbital on a neighboring carbon, and that's how we get a pi bond. This kind of overlap shows up in double-bonded molecules, like ethene. In sp2 hybridization, 1s orbital contributes about 33%, or 1/3, and 2p orbitals make up the remaining 67%, or 2/3. Now, these 3 sp2 orbitals don't just sit anywhere. They spread out as far apart as possible to minimize repulsion. The result? They arrange themselves in a trigonal planar shape with bond angles of about 120 degrees. This specific geometry is what gives molecules like ethene their flat, triangular structure. In sp2 hybridization, the 3 sp2 orbitals arrange themselves in a trigonal planar shape, so all atoms bonded to the carbon lie in the same plane. 1p orbital stays unhybridized, and this allows sideways overlap with another p orbital, forming a pi bond. Together with the sigma bond, this creates a double bond between the 2 carbon atoms, and here's the key difference. Double bonds don't rotate freely. They make the molecule flat and rigid, unlike the tetrahedral and flexible structures you get with sp3 hybridization. That's why molecules like ethene are flat, thanks to sp2 hybridization and the pi bond. Finally, let's look at sp hybridization and how it shapes molecules. Here, 1s orbital and 1p orbital mix together, forming 2 equivalent sp hybrid orbitals. But here's the key part. 2p orbitals stay unhybridized, and they're oriented perpendicular to each other. This setup allows the carbon atom to form 2 separate pi bonds, which is exactly what we see in triple-bonded molecules like ethine. In sp hybridization, 1s orbital and 1p orbital each contribute 50% to the mix. And these 2 sp orbitals don't just sit anywhere. They arrange themselves in a straight line, forming a linear shape with a bond angle of 180 degrees. This specific orbital setup is what gives molecules like ethine their rigid, linear structure. So why does that happen? In sp hybridization, the 2 sp orbitals spread out in a straight line, which means all the atoms connected to the sp hybridized carbon sit right along the same axis. But here's the key part. 2p orbitals stay unhybridized, and they're not just hanging around, they overlap sideways, forming 2 pi bonds. Add that to the sigma bond formed by the sp orbitals, and you get a triple bond between the two carbon atoms. That's what locks the structure into place. No rotation, no flexibility, just a strong, straight, linear molecule. Even though sp3, sp2, and sp orbitals all come from the same hybridization process, their sizes aren't exactly the same. That's because each type has a different mix of s and p character. And this difference isn't just a small detail. It actually plays a big role in determining bond length and bond strength. The more s character an orbital has, the closer it pulls the bonding electrons toward the nucleus, making the bond shorter and stronger. So this variation in hybrid orbital size and composition affects everything from molecular geometry to stability and reactivity. In other words, how these orbitals mix directly shapes how a molecule behaves. All right, now that we've gone over the basics of hybridization and how it changes orbital structure, in the next lesson, we'll zoom in on bond lengths and bond strengths and see how these differences show up in real molecules. That's it for today. Thanks for watching, and I'll see you next time on Chem Story.